activity. Decided to pass that out earlier this time, and we'll kind of see how this goes. So we'll kind of continue on with the slides. So we're dealing with the extraction lab today. So we've seen solubility. In theory, you should start to be extremely comfortable now with being able to identify what types of bonds are within a structure and then applying those bonds to figure out what kind of forces that those bonds could exert on something else. Okay? In theory, you should be really, really good at this. So let's kind of see how this works. If we take a look at the lower left-hand corner, we've got a series of molecules. We've got water, which gives you what type of intermolecular force? We get hydrogen bonding as far as an interaction goes. Okay? To the left of that, we have diethyl ether, which gives us what type of intermolecular force? This one is trickier, I will admit. So what types of bonds do you see in there? Hearing some CH, some CC. There's also a CO in there too, right? Of those bonds, which one do you think would be the most important to evaluate? Probably the CO because it's the most polar. Okay? So we could go through and say that diethyl ether has a dipole-dipole. We now also have to take into consideration its structure. Okay? And if you look at that structure, it's extremely symmetrical, and it's got ethyl groups, or a bunch of carbons and hydrogens on opposite ends of that oxygen. Those effectively hide the center oxygen, meaning while we do get some dipole-dipole interactions, they're fairly weak, and we're primarily looking at LDF forces, or London dispersion. Okay? So it's important to recognize that dipole is there. It's just not going to be as large as we would hope. Okay? So based on these two, okay, would I expect those two substances to mix? Should water mix with diethyl ether? Or should it be miscible? What do you think? Solubility was based on the rule like forces dissolves like forces. Is a hydrogen bonding interaction similar to London dispersion interaction? Okay, partial solubility, but we're getting fairly disparate as far as those types. So we're going to expect a fairly low solubility. We might expect to see some, but not a lot. Okay? As far as the lab goes, so you can predict, and now you then go into lab and see what actually happens. And when you move into lab, you find out that those, for all intents and purposes, are insoluble. They don't mix very well at all. Okay? So now we can make it even more difficult and add yet another substance. Let's take a look at benzoic acid. What intermolecular force would I expect that molecule to produce as the strongest force? Okay, for it to be ionic, what types of bonds do we need to have? We'd have to have ionic, and we don't have metal and a non-metal, and we don't see ions, so it can't be ionic.
There's a dipole-dipole.
So we see dipole-dipoles. If we've got dipole-dipole, let's take it a step further and see if we have the potential for hydrogen bonding. For hydrogen bonding, we have to have a hydrogen physically bound to oxygen, nitrogen, or fluorine. Do we have that? Yes, which means what type of interaction? We're likely looking at hydrogen bonding. Of course, nothing can be easy. What is this giant section out here? Okay. It's a benzene ring with a lot of carbons, a lot of hydrogens. What type of polarity are we looking at within that? London dispersion forces. Okay. So it's kind of a general rule. If we look at 4 to 5 carbons outweigh the effects of a hydrogen bonding interaction. So while it does have hydrogen bonding, we have those 4 to 5 carbons that are enough to overwhelm the hydrogen bonding aspect of the molecule, and we end up seeing London dispersion forces. Okay? So now based on that, where would I expect benzoic acid to be soluble? In water or diethyl ether? In the diethyl ether, which we end up seeing to be true when we move into the lab. Okay? So we saw a variety of applications. We could separate solids from liquids. Okay? based on their solubilities. We could go through and deal with recrystallization, where we can remove small amounts or large amounts of insoluble or soluble impurities, so extreme cases. And then we could also remove small amounts if we have a similar solubility, but it's only small amounts when we deal with recrystallization. So we have to come up with a technique in case we come across the situation where we have two compounds with very similar solubilities and then also in very large amounts. Okay? And what we're going to deal with there is what I'm terming active solubility or chemically active. What we're going to go through and do is chemically alter the compound in such a way that we can change its solubility. Okay? So we've got a couple images that we can deal with here. So first off, we're going to take a test tube, which is not a test tube, a centrifuge tube, which is what you're going to do in lab. So you'll take this 15 mil centrifuge tube and you're going to add diethyl ether to it and water. Okay, should those mix? We can go backwards. Should those mix? No. Okay. Which layer would we expect to be on top? Okay, so we're hearing all sorts of answers. What should we be looking at to figure out which layer should be on top? The densities. So it doesn't matter if it's organic, inorganic, blue, yellow, green, black, whatever you want to call it. It only comes down to the densities. So what we'd have to do is look up the densities. And if you looked at that handout, you should notice that diethyl ether has a lower density than water, which means I've got these organized very neatly. Okay, diethyl ether's on top. You would have thought I planned it. Okay, and water's down below. We can then take a look at this compound, which is ethyl 4-aminobenzoate. Which layer would that be predicted to be soluble in? Okay, so we could look at our forces. What's the strongest intermolecular force that this molecule can exert? We've got hydrogen bonding out on that nitrogen, but we've got a lot of carbons. Those carbons overwhelm our hydrogen bonding interaction. Which layer is it soluble in? Our organic. We got to write ether, and since you said organic, now I got to write organic. Or organic as well. Okay? So our goal with active solubility is to get it to change its solubility somehow. Okay? So we're going to have to somehow tweak this molecule, react it with something to make it water soluble. Okay? So what we could go through and do is add more polar bonds. So I could go through and individually add a whole bunch of OH bonds to this. Okay? And if we do that, we've effectively overwhelmed now that carbon count. And we could say, yeah, sure, this compound's water soluble. So what's the problem with that? How easy is it to put all those OH groups on there? Not so easy. Okay? So we need to come up with some other version of chemistry to allow us to do this. Okay? And what we're going to rely on, let's see if this works, is this simple reaction here. We'll add H+. Okay? Is H+ a stable compound or stable molecule? No. Why is it not stable? Because why? Sorry, I missed that. Positively charged. It's got charge. Charge is bad. How do we stabilize a positive charge? Okay. To stabilize, we have to make it more neutral or closer to a zero charge. How do you make something that's positive closer to zero? Add a negative. So we now need to go through and look at our structure, find something negative. Is there anything negative there? Where might you find negative things? Oxygen, nitrogen, all of those are valid options. Which one's the correct answer? Turns out it's the nitrogen. And our nitrogen will share its electrons with that hydrogen. Okay? In the process, what have we done? We've now formed a bond between the nitrogen and that hydrogen, right? Because we shared electrons. What's the other result of that? What happened to that nitrogen up there? It became charged. What's another name for positive charge? A cat what? What type of force might we see from that compound? Ionic bonding. What's a classic example of any compound that has, or a classic example of an ionic compound? Let's try that. Salt. What do you know about salts? They dissolve really well in water. So as soon as we form an ionic compound, we've now made something water soluble. Okay? So by simply adding that hydrogen to this structure, we've made the structure charged, and it is now water soluble. Okay? Whereas before it was not. So we have altered and changed the solubility of the compound by running this reaction. What type of chemistry have we performed in this single step? Acid-base chemistry. Okay? That's the chemistry we're going to take advantage of with the extraction technique to try and figure out or to purify things. So why should we do acid-base chemistry for extraction? Well, primarily it's simple. Okay? It's also extremely fast. It's also reversible. Okay? And then taking a step further, it's also predictable. So we get lots of possibilities here for things that make this type of a reaction advantageous to us. So we could look at those two examples. If I take water, okay, yeah, I know it's already water soluble, but let's say it's water. We want to make it more water soluble. To make it more water soluble, we have to make it more charged. Okay? So we could add acid to it to make it H3O+. Okay? If I want to reverse that reaction, what do I need to do? I can add a base. Okay? So by reversing the reaction, all I got to do is add the opposite species. Okay? We can also then go into predictability. Okay? And trying to figure out which direction our reaction is going to go. We need to make sure it favors the direction that we want. Okay? And this is where I like to bring in what I call the DA face test. Okay? Given the option, let's compare HCl and H3O+. Can anybody tell me, particularly if you took 151, what you know about HCl? Or sorry, 113. Anybody? What can you tell me about HCl? It's not just a pretty strong acid. It is defined as a strong acid. Okay? So we know that that is an extremely dangerous species because it is one of the strong acids. What can you tell me about H3O+? It's not as strong an acid. Okay? Why is that important? Well, here's where the face test comes into play. Which would you rather have splashed in your face? HCl, which is by definition a strong acid, or H3O+, which isn't quite as bad. H3O+. Chemistry is going to do the exact same thing. It's going to push the direction that's opposite our strong acids. It's going to favor the weaker acid. You could also do it with bases. It will favor the weaker base. Yes?
The weaker base or the weaker acid is more stable?
Yep. It also comes back to stability. Okay? The weaker acids, the weaker bases are more stable, lower in energy, less reactive. Any one of those terms all go back to the same idea. Okay? So we could look back at the structure that we were playing around with earlier and trying to decide which of those nitrogen or which of those atoms is the best place to get electrons from. We got our nitrogen or our oxygens. And what we'd end up doing is evaluating the strength of the acid in each of those cases and trying to decide which one of those is the weakest acid, because that's going to be the one that's favored. Okay? How could we come up with that? Since you skipped that chapter conveniently in lecture, this makes it a little bit more difficult. There's a couple ways that we can go through predicting this. Okay? What we'll end up doing is comparing our acid strengths across the reaction. So we could compare and say this first case,